Let's consider the reaction of this compound. If we're going to do nitration, it's going to react with NO2+. We can have attack at the ortho position. Again, we have attack at the ortho position. If we do this, we produce the carbocation that is ipso. Okay, this is the ipso position. Ipso to the oxygen atom. That is, it's on the carbon that the oxygen atom is attached to. Well, look at what happens. Well, immediately that carbocation can resonate with the lone pair. This gives us a resonance form here. This resonance form now delocalizes the carbocation from the carbon onto the oxygen, making an oxonium ion. But of course here, all the atoms have an octet of electrons. So that means that this resonance form, this intermediate, is especially important, and the intermediate is especially stabilized. Now, I can also resonate this around the ring, and there are other resonance forms that can be drawn. Now, notice the position of the carbocation that we formed. The first carbocation, intermediate, is ortho to the added nitro group. It's always going to be that way. Then when we resonate it around the ring, you see the carbocation is para. Now there's another one that puts it ortho again. I'm not going to draw that one, but you draw that one today for your exercise. So that's attack at the ortho position, and we see how the substituent with the lone pair stabilizes the intermediate for this reaction. That means stabilizing it lowers the energy. That's going to lower the activation barrier by the Hammond postulate. Now, it can also attack meta. If meta attack occurs, we get this intermediate. Again, notice that the carbocationic intermediate formed is ortho to the substituent that's coming in. Now, this one can resonate again. Notice the carbocation formed is now para to the incoming substituent, and there's another one, and I'll leave that again for you as an exercise to put it to the other ortho position. The key here, though, to note is that never is that carbocation ipso to the oxygen, and being ipso to the oxygen is required for me to draw a legitimate resonance form that invokes the lone pair on oxygen to stabilize this carbocation. Like the octet, the resonance form that has all octets was especially stabilized up above. So the meta here When attack occurs at the meta, we do have resonance stabilization, but we don't get the oxygen, the pre-existing, if you will, substituent, can't get into the party. It can't contribute, it can't participate, and so you don't get any special stabilization of the meta attack. So the meta attack is going to be, the intermediate is going to be higher in energy, which means a higher activation barrier. Now, by the way, all of these are kinetic ratios, right, that we're dealing with. They're not the thermodynamic ratios. And then the final one here is the attack can occur at the para position. If that occurs, we get an intermediate. That has a carbocation ortho to my incoming substituent. But look what happens when I resonate that system. Just spread the charge out. Now the charge is para to my incoming substituent. But look what it also is. It is also ipso to my oxygen atom, which means that the lone pair from oxygen can get involved in the stabilization. We delocalize out onto the oxygen atom. Of course, there's another one here that has the carbocation back around on the positive side. So everything here has an octet. And having an octet means it's especially stable. The positive charge we see for the para attack is distributed onto more atoms. 6 of the ring, or 5 of the ring, plus the oxygen would be 6. Whereas here, it's only the 5 atoms, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 of the ring. You can't get the oxygen involved. For the para attack and the ortho attack, we see this resonance form that distributes the charge onto the oxygen. It also has an octet for all the atoms, both of those contributing to stability. The other is the number of resonance forms. 1, 2, 3, and the one I asked you to draw, 4. 1, 2, 3, and 4 for the para position. And of course the meta, you only have 3. So again, these intermediates for ortho and para attack are especially stabilized. The activation barrier comes down. The rates of reaction can go faster because the barrier is slower. Remember kinetics versus thermodynamics. Kinetics, the rates of reaction, are dependent upon those activation barriers. So all the substituted benzenes that have an atom with a lone pair, so the halogens, the oxygens, nitrogen is actually a better donor than oxygen. So you take as an exercise to draw these with aniline. Okay? You see the lone pair on nitrogen. Nitrogen is actually less electronegative than oxygen, so it's better at sharing its lone pair. So you draw these substituents for nitrogen. Also show the distribution of that lone pair of nitrogen around the benzene ring in the ground state of the molecule, the starting material product, starting material of the reaction, so that you can see these principles that we've just illustrated.